Welcome to Bodhi Academy. My name is Amisha Palaso, and today in this video we'll continue with the chapter Force and Pressure of Class 8, Chapter 8. So previously in this chapter, we saw that force is defined as a push or a pull of an object. So the motion of the object is due to the force that is being applied onto that object. Further, we saw that without any interaction between any two objects, there will be no motion of object that will be happening. So interaction of one object with another object results in the force between the two objects. Only on application of this force, further the object will displace or be in motion. Forces applied on the same direction and to one another. So if two people are applying some kind of force onto an object from the same direction, we said that those forces are going to add up together. But if somebody is applying a force from the right side and the other is applying force from the left side, so then the net force over here will be the difference between the two forces that are being applied. When force is applied in the same direction, we said that the speed of the object in motion increases, and when the force is applied in the opposite direction, the speed of the object in motion decreases. Then we saw that force can bring a change in state of motion of the object. So state of motion, when we said, we considered the direction. The direction can be changed of the object when force is applied, as well as the speed can change. Force can also bring about a change in the shape of the object. So in today's class, we'll see what are the different types of forces, contact and non-contact forces, electrostatic forces, gravitational forces. Then we'll see about pressure and the pressure exerted by liquid and gases. And finally, we'll talk about atmospheric pressure. So contact forces. Can you push or lift a book lying on a table without touching it? Can you lift a bucket of water without holding it? So what they are saying is that now say there is a book on the table. I want to push it apart. So is it possible that without touching that book or without holding a bucket, will I be able to move or lift any object? No. I have to be in contact with that object, right? So without that, what we said previously was when there's no interaction, means there has to be some kind of interaction between me and the book so that the book moves. Otherwise, if there's no interaction, if I'm not even touching the book and I'm just like waiting for it to move from there, it won't move. I have to apply some kind of contact or some kind of force to it. Generally, to apply a force on an object, your body has to be in contact with the object. So to move something, now say I have to lift this book from here. So I need to hold the book to lift it up. If I keep it down and I expect it to move, it won't move or it won't come up by itself, right? So there has to be some contact between me and the object. The contact may also be with the help of a stick or a piece of a rope. So now say there's something on the road, sometimes what we do, we just kick it with our feet, or sometimes we take a stick and we just move it aside. So that is what is happening here. So the contact doesn't only have to be a human contact, not only like I have to go and touch it and move it. No, it can be a contact with any other object also, like a stick. When we push an object like a school bag or lift a bucket of water, where does the force come from? So now when we are doing all of this pushing and lifting, where is that force coming from? So that force comes from the muscles. So this force is caused by the actions of the muscles in our body, and therefore this force resulting due to action of muscles, it is known as the muscular force. So that force which acts upon due to the muscles in our body, due to the action of the muscles in our body, that is known as the muscular force. Animals also make use of muscular force to carry out their physical activities and other tasks. So now we have seen, like we see blocks, then we see donkeys, we see goats, horses, camels. All of them, they are used as carriers. They carry camels. When we see, they carry humans. Even blocks carry humans. Donkeys carry so much of our what to say, luggage and all at times. So we have seen that. So in that case also, animals are using their muscles. in a similar way so as to we do. So in performing these tasks, they use their muscular force. Since muscular force can be applied only when it is in contact with an object, it is also called a contact force. So now what they are saying is that when muscular force, now since muscular force is only applicable if I have to move something, my muscles are going to be in action. So that is what my muscular force is being applied. So muscular force is basically what there is some kind of contact between me and the book that is happening to push that. So because there is some kind of contact, then it is known as contact forces. Contact forces only occur when there is some kind of contact between me and the object. So are there other types of contact forces? Now let's see. Friction. Recall some of your experiences. A ball rolling along the ground gradually slows down and finally comes to rest. When we stop pedaling a bicycle, it gradually slows down and finally comes to a stop. A car or a scooter also comes to rest once its engine is switched off. Similarly, a boat comes to rest if we stop rowing it. Can you add some more such experiences? So now what we are talking here is that, see, now say I hit a strike, I kick the ball. Will the ball never stop moving? No, at some point it will come to rest. Now if I want to keep it moving, what we said, if we have to increase the speed of that ball moving, we have to apply more force. But I'm saying not applying any force, I just kicked it once and then left it. So after some time gradually it will slow down. Even for that matter, our bikes and all, when we switch off the engine, after some point it comes to a rest or it comes to a stop. So now why is this happening? In all these situations, no force appears to be acting on the objects, yet their speed gradually decreases and they come to rest after some time. So now what they are saying is that here now there is no stopping force for them, right? Now that I kick the ball, somebody is stopping the ball with their hands. No, it is just its speed decreases automatically and it comes to rest. So what causes a change in their state of motion? So why is this happening? Can you guess the direction in which the force must be acting in each case? What we have said, we have discussed this before, that if you have to stop something, like see, say a player hits a goal, okay, and the goalkeeper stops it. So the goalkeeper, what he'll do, he'll apply a force in the ball will be coming towards him, right? So he'll apply a force in the opposite direction. He won't push the ball towards the goal. No, he will apply a force in the opposite direction. So here we have to apply a force in the opposite direction to stop any incoming objects. So the force responsible for changing the state of motion of objects in all these examples is the force of friction. So now the invisible force that is acting upon all of these things, there is no visible force. I am not going and stopping the ball, I am not stopping the bike with my hands, it just stops, it comes to a halt. So this invisible force that is acting up on these objects is known as friction. So now friction, it is the force of friction between the surface of the ball and the ground that brings the moving ball to rest. So now friction is what? It is that force between the surface of the ball and the ground. So there is some kind of force that is acting between the ball and the ground that is bringing the ball to rest. Similarly, friction between water and boat brings it to stop once you stop rowing. The force of friction always acts on all the moving objects and its direction is always opposite to the direction of motion. So the force of friction, this invisible force of friction is always there, okay? And it acts on all moving objects. The minute you stop applying force, there will be some kind of force between the object and the surface on which it is that will stop the object from moving. So that is this force of friction. And this force of friction, it is always in opposite direction to the force that you are initially applying. If I have applied a force from right, the other stopping force or force of friction will be from the left side. Since the force of friction arises due to contact between surfaces, it is also an example of contact force. So now friction is also an example of contact force. Why? Because now when we said that the ball, there is a kind of force between the surface of the ball and the surface of the ground. So means what? The ball was not in the air, the ball was on the ground. So there was some kind of contact between the ball and the ground. So it is also an example of contact forces. So you may be wondering whether it is essential for the agent applying a force on an object to always be in contact with it. So now what they are asking is that is it necessary? Now all these forces that we have talked are when both the objects are in contact with each other. So is it possible for any non-contact forces to be there? So now let's see. So non-contact forces. So here now say what they are saying is that you have a magnet. Okay, you say you have say two magnets here, bar magnets. Okay, and on this one of the magnets, say I place some pencils or some kind of stuff I place on it. Okay, now say this is the north and this is the south, and say there's another situation, same situation. This is what? This is north and this is north. Again we have the pencils placed over here. Now what will happen in these two cases? So now here what we'll do, we are talking about non-contact forces, and here these are the magnetic forces because there are two magnets involved here. Now what will happen when we bring this magnet close here? See, the moment I start bringing this magnet close, the south side of the magnet will be attracted. So slowly this will start moving closer to the other magnet, right? But we have to not touch it. We don't have to touch both the ends of this magnet. So we are going to gradually get this closer to this side of the bar magnet, and we'll see that this magnet is going to get slightly pulled by itself. And when we look here what will happen is that here now when I try to get this magnet close to this one, this magnet which is there, it will start moving up. This will go even more far. Now why is this happening? So we know that when two, we say that what there's a common rule that like they repel and unlike attract, right? Okay, so what is happening here is that this like terms which are there, this, see, when we got this magnet, this side they had both the north parts of the magnet facing each other. So in this case what was happening was there was repulsion that was happening. Okay, but here you see there is north and south, so these opposites, they are attracting each other. So the moment you try to go close to this one, this south direction bar gets attracted towards the north direction bar. Meanwhile here it is moving far, but here we have not touched any of the ends of the magnet to each other. So there is some kind of difference, or there is no contact that is happening over here. So thus the magnets on the rollers begin to move when the other magnet is brought near to it? Yes. So does it move in the direction of the approaching magnet? In one case yes, in one case no, it goes to the opposite direction. Does it mean that that some forces must be acting between the two magnets? Yes. So now attraction or repulsion between objects can be seen as another form of pull or push. So do you have to bring the magnets in contact for observing the force between them? No. So we didn't touch both of the magnets. Without touching only, there was some kind of movement that we could see. A magnet can exert a force on another magnet without being in contact with it. The force exerted by a magnet is an example of a non-contact forces. So in this, what we are saying is that when two objects are not in contact, that kind of forces are non-contact forces. So example we saw were non-magnetic forces. Why? Because in that like terms which are there, they are going to repel, go far from each other, and unlike terms are going to attract each other. Now we'll see electrostatic force. So now here in this activity, what they have told is, they have told take a plastic straw, cut it into two halves and keep one part of it, you attach it to a thread and you leave it hanging. Now the other part you take and you rub it on a paper, okay, and then you try to bring it close to the piece of straw that is hanging with a thread. So what you will see is there will be some kind of movement that will be happening. Now why is this happening? So a straw is said to have acquired electrostatic charge after it has been rubbed with a sheet of paper. Such a straw is an example of a charged body. So when you rub that straw with a piece of paper, there was some kind of charge that was generated and that made it a charged body. So due to that, there was some kind of movement that was occurring. The force exerted by a charged body on another charged or uncharged body is known as electrostatic force. So here now this was the charged body and this was uncharged. This you didn't rub onto a paper, right? So only this we rub. So this was the charged body. So this was charged. So what they are saying is the force that is exerted between a charged and a uncharged, or even for that matter another charged body, that force is known as the electrostatic force. Now, gravitational force. So you know that a coin or a pen falls to the ground when it slips off your hand. Leaves and fruits also come to the ground when they have detached from the plant. Have you wondered why is it so? Now see, when any time you drop something or something falls from your hand, it goes down to the ground. It doesn't float. It goes down to the ground. So now why is this happening? So when the coin is held in your hand, it is at rest. As soon as it is released, it begins to move downwards. It is clear that the state of motion of the coin undergoes a change. So now say there is a coin onto my hand. It is at rest. There is no motion of the coin that is happening. The moment I release it, the moment I drop it, it goes in some kind of motion. Okay, state of motion is being predicted, or state of motion is occurring over there and it is moving downwards. So can this happen without the force acting on it? Which is this force? So objects or things fall towards the earth because it pulls them. So now what they are saying is there is some kind of force, okay, from the earth that pulls all of these things down. So every time something falls, the earth tends to pull them towards itself. That is the reason they go downwards, not they go upwards. So this force that pulls this force from the earth, it is known as the force of gravity or just gravity. This is an attractive force. So now there's the ground, the force down, see, the ground is attracting the thing that is falling. If it was repelling, it would have gone in the opposite direction. That would it would fly. But no, it is coming down. Means there is some kind of attractive force that is occurring on all the things that fall down. The force of gravity acts on all objects. The force of gravity acts on all of us all the time without our being aware of it. See, now what does this mean? Now I'm sitting on this chair or this laptop is placed on a table. If say there was no gravity, will this laptop be still resting on this table? No, because now there is some kind of attraction, everything remains onto the ground. If there was no gravity or there was no attraction, everything would have been floating around because there is no attraction between the ground and the object that are present. In that case, we see astronauts and all, in what we say in space there is no gravity. That's why they keep floating, or their things are always in motion, or they are like unevenly floating in the air. Here it is not that case. Here everything settles to the ground because there is force of gravity or some kind of attraction from the earth that pulls all of these things to the ground. Water begins to flow towards the ground as soon as we open a tap. Water in rivers flows downwards due to the force of gravity. Now when you turn on the tap, does the water go upward? No, it goes downward. Why? Because there is force of gravity that comes from the earth. Now, pressure. So is there any relation between pressure and force? Now let's find out. Try to push a nail into a wooden plank by its head. Did you succeed? Try to push the nail by the pointed end. Could you do it this time? So now what they are saying, the nail, it has the broader part and it has the pointing part. In first situation they are telling you what? The broader part, you try to hit it into a wooden plank. Will it go? No, it won't go. Now they are telling you to reverse it. The pointed part, you keep it on the plank and you hit it inside. Will it go inside? Yes, it will go. Why is it happening so? Why did the broader part not go inside? So now try cutting vegetables with a blunt knife and then with a sharp knife, which is easier. Now they are saying try cutting with a knife which is less sharp. Will it cut? No. Will a sharper knife which has a thinner tip cut the vegetables and fruits? Yes, it will. Which was easier? Do you get the feeling that the area over which the force is applied, for example, the pointed end of the nail, plays a role in making this task easier? Yes. So the force acting on a unit area of surface is called pressure, or it is given by pressure is force upon the area on which it acts. So now say so what is pressure? They are saying is that the force acting on a unit area. So now if the force has to be more and the area on which you are acting has to be less. So in that case what we said, see, when the nail was not going inside, why? Because the area was too broad and the force was less. So in that case you need to reverse it towards the pointed side. So the area becomes less and lesser force is applicable to push that nail inside the wooden plank. Note that the area is in the denominator in the expression. So smaller the area, larger the pressure on the surface of the same force. So smaller the area, the pressure will be more on the surface of that force. The area of the pointed end of the nail is much smaller than that of its head. The same force therefore produces a pressure sufficient to push the pointed end of the nail into the wooden plank. So now, because that area of the nail was smaller, we could easily push it in because the pressure was sufficient to push that pointed tip into the wooden plank. Now can you explain now why shoulder bags have broader straps and not thin straps? So now when we see our bags, they don't have very thin straps. Why? Because the pressure then will increase. If we have thinner straps, the pressure on our shoulder will increase of the bag. So to reduce that, we have broad straps. Now, do liquids and gases also exert pressure? Does it also depend on the area on which the force acts? So now here in this what they have taken is, they have taken this pipe which is of around 15 centimeter. Okay, and its diameter is around 5 to 7.5 centimeter. And here they have taken a rubber which they have stretched and placed it at the end of that tube. So now here initially what they have done is that they have added little amount of water. See, the water quantity is less. Then they doubled the water quantity, and what they saw that the balloon bulged out even more. The size of the balloon grew bigger. So now why is this happening? See, thus the bulging of the rubber sheets in this case indicate that the water exerts pressure on the sides of the containers as well. Yes. So now, can you say that liquids exert pressure on the walls of the container? Do gases also exert pressure? So now what was happening here was that there was some kind of pressure that was being built up here. So that is why this pressure was making this rubber stretched, this ball like thing bulge out even more because there was a lot of pressure that was being generated by the liquid. So now does this even happen in gases? Do gases also exert pressure? Do they also exert pressure on the walls of this container? Let us find out. When you inflate a balloon, why do you have to close its mouth? What happens when you open the mouth of an inflated balloon? So now when we blow a balloon, we blow and do we keep the end open? No, we close it. Why? Because the air is going out and the balloon is shrinking. So the minute you open it, the air passes out and the balloon starts to shrink. So suppose you have a balloon which has a hole. Would you be able to inflate it? No. Why? Can we say that the air exerts pressure in all directions? So what happens is when you blow air inside the balloon, there is that air, it creates a pressure in all the directions. So the balloon grows equally in all directions. Is it like the balloon grows in one direction, only one part of the balloon grows and the other remains like that? No. It is being equally distributed in all directions. So therefore, when there is a hole in the balloon, okay, now say there is a hole on the right side, will the balloon grow on the left side? No, it won't grow. Why? Because there is equal pressure on all sides and therefore the pressure is being released from that one hole that is present, and so that due to that the balloon won't inflate. Do you recall what happens to the air in the bicycle tube when it has a puncture? Do these observations suggest that the air exerts pressure on the inner walls of an inflated balloon or tube? So we have to find gases to exert pressure on the walls of their container. So same happens with the bicycle tires. So the moment there's some kind of a hole that is created, the pressure really goes out and the tube goes off. Now we'll see atmospheric pressure. You know that there is air all around us. This envelope of air is known as the atmosphere. So we know the envelope of air is called atmosphere. So the atmospheric air extends up to many kilometers above the surface of Earth. So it is not only at certain level, it is there up till quite a high level. So the pressure exerted by this air is known as atmospheric pressure. So now the pressure that is exerted by this air or from the atmosphere, it is known as atmospheric pressure. We know that the pressure is force per unit area. If we imagine a unit area and a long cylinder standing in it filled with air, then the force of gravity on the air in this cylinder is the atmospheric pressure. So now say that they are saying we have this cylinder here and we let it stand. So all the air that will be inside is the atmospheric, in this cylinder will be the atmospheric pressure in this particular unit area. Okay. But how large or small is the atmospheric pressure? Let us get an idea about its magnitude. Take a good quality rubber sucker. It looks like a small rubber cup. Press it hard on the smooth plain surface. Does it stick to the surface? Now try to pull it off the surface. Can you do it? So we have seen those suction pumps which come, see, when you attach it to something and you push it inside, then when you try to pull it out, it won't come out. Why? Because there is some kind of pressure that is generated inside. So when you press the sucker, most of the air between its cup and the surface escapes out. So when you press it, there is no air inside. So the sucker sticks to the surface because the pressure of the atmosphere acts on it. So the moment you press it, air escapes out, the sucker sticks to the surface. Why it is sticking? Because there is some kind of atmospheric pressure that is falling onto it. To pull the sucker off the surface, the applied force should be large enough to overcome the atmospheric pressure. Now, if you have to pull it back, it has to be larger than the atmospheric pressure that is being put onto that sucker. This activity might give you an idea about the magnitude of atmospheric pressure. In fact, it would not be possible for any human to pull the sucker off the face if there were no air at all between the sucker and the surface. So if you try and remove all the air, like literally zero air, make it zero air over there, and you try to pull it, we won't be able to pull it. There has to be some kind of air that is there so we can pull it back. So that means what? There is a large amount of atmospheric pressure that is working on that sucker. The force due to air in the column of the height of the atmosphere and the area 15 into 15 centimeter is equal to the force of gravity of an object of mass 225 kg. The reason we are not crushed under this force or gravity is that pressure inside our bodies is also equal to the atmospheric pressure and balances the pressure from outside. So see, so much of force of gravity is acting up upon us. So what they are saying is that which is approximately 2250 Newton. So now, why are we not crushed yet? Actually, technically we should have been crushed, but what they are saying is that even our body has equal amount of atmospheric pressure, and therefore that pressure from our body balances out this pressure. Okay. So that was it for this chapter. So what we have learned so far is force could be a push or pull. The force arises due to interaction between two objects. Force has magnitude as well as direction. Change in speed of an object or direction of its motion or both implies a change in state of motion. Force acting on an object may cause a change in its motion or change in its shape. A force can act on an object with or without being in contact with it. The force per unit area, it is called a pressure. Liquids and gases also exert pressures, and the pressure exerted by air around us is known as the atmospheric pressure. So thank you so much for watching today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.